We're going to look at division today of radicals. And what I want to do is look at four types of division problems, and they're each handled just slightly differently. Here's the first one. If we take a look at something like the cubed root of, let's say, 50 x to the 8th in the numerator divided by 27y to the 12th in the denominator. Let's take a look at this problem, right? Well, here's what happens in this problem. It turns out there isn't anything that I could cancel. I would if I could and maybe create a single term. So how else am I going to get rid of this fraction under the radical sign, which I'm not allowed to have in a final answer of a simplified radical? Well, what I'm going to do is separate it, and I'll have the cubed root of 50x to the 8th in the numerator and the cubed root of 27y to the 12th in the denominator. And then I see if I could simplify these radicals independently, and I can. There's no perfect cube in 50. No factor of 50 is a perfect cube. So I'll go ahead. The x to the 8th has enough x's, though, to take a cubed root of at least some of them. So I'll put x to the 6th here, because 6 will divide. It's the biggest number of x's up to 8 that divides evenly by 3. And then I'll multiply. I'm using the product rule here in the numerator, and I'll multiply by 50x squared, the remaining part of the 50x to the 8th that will multiply by x to the 6th and still give me 50x to the 8th. And then on the bottom, this turns out this is already a perfect cube under here, so I won't need to rationalize like I will in my problems that are going to come up a little bit later. But this is already 3, because the cubed root of 27 is 3, and y to the 12/3 would be y to the 4th. Let me just finish the numerator off. I could take the cubed root of x to the 6th. That's why I moved 6 of the x's over there. And I get x squared here times the 50, the cubed root. And by the way, I forgot to put the index there of 3. But the cubed root of 50x to the 2nd all over 3y to the 4th. So that's our first type, where we had a fraction under the radical, and when we separated it, this already was a perfect square under there, or perfect cube under there, right? Okay, so now what's another type that can occur with division of radicals? Well, what if we had something like this? We had a radical in the top and bottom, so we have division. But it turned out that we had radicands that could completely cancel out factors such that we have a single radical. Here we wouldn't need to rationalize either, because the fact that we have division here is going to go away just by the fact that 54 divided by 6 is 9, still under the radical, and x to the 3rd over x to the 1st is x to the 3 minus 1, or x squared. So I have a single radical. I've taken care of the fraction part, and I can go ahead and take the square root of 9, which is 3, and the square root of x squared, which is x. So this is a second type where we were able to cancel and not have to deal with a radical in the denominator anymore. Okay, so the next one. I would say these two problems, by the way, these come out of 10.4. I would say these were section 10.4 kind of problems in our book. And then the next ones are where we have to rationalize, and I would put these in the 10.5 section of our book, and they'd be problems like this. For example, if we had a problem where we had a fraction under the radical, but unlike here where it canceled, we don't have a choice. They did not cancel. So let's try to separate it like we did on the first problem, right? If it didn't cancel, we separated it. But there is a difference, though, in that problem as well, because here, once we separate, it turns out that that radical in the denominator won't just go away by itself. I cannot take the cubed root of xy squared like I could take the cubed root of 27y y to the 12th. So here is where I have to rationalize, and what that means is I'm going to have to multiply the top and bottom by a form of 1, where that form of 1 will allow me to go ahead and cause this to become a perfect cube under here. Well, let's think about what that would take. Well, here I have x to the first. I'll need x to the second in order to be able to have a perfect cube under the radical in the denominator, right? I'll end up with x to the third. And how about y squared? Well, I need one more y, so I'll multiply the top and the bottom by y under the radical. And now what happens is I end up with this new problem of the cubed root of 3x squared y in the top and the cubed root of x cubed, right, x times x squared, y cubed in the bottom. And now I could go ahead and simplify that radical in the bottom. The top doesn't have anything I could simplify, or I would do that as well. And this bottom will simply become xy, because the cubed root of x cubed is x and the cubed root of y cubed is y, right? Okay, we might try a second version of that. Let me see if I can give you a similar problem. Let's say we had this. And here's the situation. Okay, let's say we had something like that. Well, okay, so, boy, it might be tempting to do some cancellation, but the truth is I cannot cancel this x and that x because this term up here is not under a radical sign. So I can't do that. So what are my choices? Well, here I have a radical that, in this case, I guess 8 is a perfect cube. I would be able to take that part of it out. But I don't have enough x's and I don't have enough y's in order to be a perfect cube. So I would have a situation, in fact, I'll tell you what, I think I'm going to change this problem. Let's say that this originally was something else like a 2 under here. So even that was not a perfect cube, okay? And let's go from there. I think that would probably be a problem that maybe more folks would struggle with in the homework. So let's take a look. Well, so even this 2 is not enough. So we're going to need to come up with a product here of the top and bottom so that we can get a perfect cube underneath. Well, if that's a 2, the perfect cube that involves a 2 that I could think of would be 8. 8 is a perfect cube, and 2 times 4 would get me that 8. I need 2 more x's because this is only x to the first, so I'll multiply by x squared. And this is y squared, so I'll multiply by an additional y. And I'll multiply the top by the same amount. Okay, so the top is just going to be what I have there, x y squared times the cubed root of 4x squared y. But the bottom now, we have what we call rationalized it, right? We have created a perfect cube under there. And by the way, this index could be anything. We just happen to have 2 problems where we're dealing with cubed roots, right? So we're going to go ahead and get what here? Let's take a look. We'll get 8x cubed y cubed. And now we could simplify that denominator into just simply the cubed root of 8 is 2, cubed root of x cubed is x, cubed root of y cubed is y, and the top has this in it. Well, this actually gives us another opportunity for simplification because both of these terms are outside of a radical. So I could do some canceling. I could cancel this x with this x, and I could cancel one of these y's, that's y squared, with this y. And so my final answer is 2, there is one y left here, is 3y times the cubed root of 4x squared y all over 2. I mean, there could be all kinds of slight variations. For example, if this radical did have some cube root and some cube in it, I could take the cubed root of it, right? But in this case, this is simplified because of the following things. I have no terms under here that have powers greater than or equal to the index. I have no radicals in the bottom. And I have no fraction that contains a radical like this problem originally did, right? So I'm good. This is simplified. Okay, let's look at one last problem where we have rationalization needed, but we have a binomial in the bottom. So we're not allowed to have radicals in the bottom at all, but the way you get rid of a radical when you have a binomial is you multiply by what is called the conjugate, as far as creating a multiplication of a factor of 1, where I multiply the top and bottom of the original problem by the same thing. So I'm going to multiply this top and bottom by what's called the conjugate of the binomial, which is the same binomial with the opposite sign. And when I do that, what's going to happen is, through FOIL, the radical will always get eliminated. That's supposed to be a 3 there. My parentheses kind of got in the way of the 3. But that's the square root of x minus 3. Okay, so let's go ahead and do this. We're not going to go ahead and distribute the top, because I'm kind of hopeful that there just might be a factor that comes out of the bottom that we could cancel with the factors of the numerator. So that's why I want to leave the numerator in factored form. But let's see what happens here through this multiplication. So the square root of x times the square root of x, I'm using the f of FOIL there, would be the square root of x squared. The outside is going to be minus 3 times the square root of x. And the inside is going to be plus 3 times the square root of x. And they're going to cancel each other out. This is one of the reasons that what we did in multiplying by the conjugate causes all the radicals to cancel. These middle terms cancel. And this radical is going to work itself out. The square root of x squared is x, but we'll deal with that in the next step. And then the L of FOIL will be minus 9. Okay, so what I get now is 6 times the square root of x minus 3. This is going to become x, and this is minus 9, and the middle terms canceled each other out. I think I'm done, because I think I don't have any factors that could cancel. I can't factor this. If this was x squared minus 9, that would factor, but nothing is going to go ahead and cancel here. I think we're done.